Welcome back. Manufacturing processes MEFP 2013213 manufacturing processes students. Okay, so today we're going to talk about a new topic, non-traditional processes and powder metallurgy. Okay, so if you recall, yeah, all this while we were talking about the general, or we should call it the traditional processes in manufacturing. We spoke about metal cutting, sand casting, lathe, milling, drilling, die casting, yeah, hot chamber die casting, cold chamber die casting, low pressure casting. Okay, we spoke about welding, abrasive grinding, hot working, cold working. So if you recall, all this involves some manual handling, and the dimensionals were generally, or the dimensionals of your product were generally a standard dimension. Yeah, so when you machined or you molded or you shaped, it was a standard dimension products. So if this time you did not get to go for your manufacturing processes industry visit, but in the previous semesters, if you asked your seniors, those who had visited the manufacturing industry, most of them would, actually all of them would have reported visiting industries that worked with traditional machining processes. So they had either seen some form of die casting or some form of sand casting, some form of metal casting that it was done or performed in these industries. So where does non-traditional processes come in? Yeah, so non-traditional processes, or we call it modern processes, is a step further. So it will involve automation of the manufacturing plant, or automation of the product and process itself. So you have machining, cutting, but it will be done in a performed in an automated way for more precision and accuracy. So if you look at the description, non-traditional processes is the machining processes to remove materials by chip formation or abrasion. So you're still going to remove material by chip formation or abrasion, but how are you going to remove material? So these processes led to the development of other advanced processes called non-traditional processes. Okay, so there are at least four types of these non-traditional processes. You have under the category of mechanical, ultrasonic machining. Under the category of chemical, example is chemical milling. Then you have electrochemical. Under the category of electrochemical, you have electrochemical machining. And under the category of thermoelectric, you have laser beam machining. So ultrasonic machining, what is ultrasonic machining? So first of all, how does it look like? So this is your ultrasonic machining. Yeah, so ultrasonic machining, if you look at it, it's made of a transformer. You have a transformer, and you have a transducer coiled around it. What does a transducer do? Okay, so this entire system is connected to high frequency current. Transformer generates current, yeah, steps up, steps down the current. Transducer, what does it do? Transducer controls the oscillating motion of the machine itself. Okay, so with the presence of transducer, this whole structure can, or the tool can move, can oscillate at 20 kilohertz. Okay, then you have, when the tool, or when the transformer and transducer oscillates, you have some kind of vibration. You have a tool holder. Okay, and you have a tool. This is your tool holder, this is your tool, this is your workpiece. Okay, and your workpiece is immersed in an abrasive slurry. So what is this abrasive slurry made of? So all this time, you're looking at your machining, and your product would be either you use a solid a solid slurry. Like if you remember, in abrasive and grinding processes, we use abrasive powder, and then we rub the surface using leather in under the lapping process. Yeah, we did use a mandrel with embedded abrasive stones to grind the inner surface of a hole. So all this while we looked at solid abrasive particles like abrasive stones, abrasive powder. But now in ultrasonic machining, we are going to look at abrasive in the form of liquid. So here your abrasive slurry is made of a mixture of boron carbide, silicon carbide, and aluminum oxide. So boron carbide, silicon carbide, and aluminum oxide. So going back to the description, yeah, how does this ultrasonic machine works? Yeah, so the principle of ultrasonic cutting is done by abrasive grains. So here you have, I just mentioned to you, your slurry is made of boron carbide, silicon carbide, and aluminum oxide forced into the workpiece by linear oscillation of a tool. The abrasives are the cutting edges of the tool, and they are carried by a liquid that flows between the workpiece and the tool. So once that is done, okay, so once you immerse your workpiece in the abrasive solution, if you remember, I showed you the transducer. The transducer causes the attached tool to oscillate linearly. So here the transducer causes the tool to oscillate linearly at 20 kilohertz with a very small amplitude. Yeah, so the tool oscillation is produced by being a part of a sound wave energy transmission that causes the tool material to change its length of contraction and expansion. So what happens is transducer causes the tool to oscillate. So when the tool oscillates, it's going to oscillate. It's going to create a vibration, and it's going to oscillate your object. And you would find that the oscillation would cause the workpiece to oscillate, and since it's immersed in the abrasive slurry, the abrasive slurry will be stirred, and it's going to rub against the surface of your workpiece, and it's going to help to remove material. So here the job is done not by the tool. Yeah, the tool is not actually performing machining. It's the abrasive slurry that is assisting in the machining process. Okay, so like I mentioned to you, the workpiece is immersed in an abrasive slurry. Abrasive slurry is made of boron carbide, silicon carbide, and aluminum oxide. Okay, so that is an ultrasonic machining. So how do you know how much of material is being removed? This entire structure is connected to a mainframe. So the mainframe can automatically control the amount of material removal in the x-axis, or it can monitor the amount of material removal in the x-axis, y-axis, and z-axis. So what are your tools made of? Tools are made of brass or steel. So the tool shape is made of surface to be machined. So what are the advantages of ultrasonic machining? There is absence of thermal stresses. There is no it's unlike the normal machining process. Yeah, when you machine, you generate a lot of heat and you need to use coolant and blah blah blah. Here there is no thermal stresses. There is no heat generated because you are doing, or you're machining using an abrasive material. Yeah, there is low cost of tools, and you do not need to employ high skilled people. Okay, so a normal person can perform the operation because this is an automated process. You do not need skilled people to run this machine. Okay, it's all automated. As long as the automation part is fixed, just with the push start of a button, it will automatically perform the job. However, just like any other machining processes, it comes with disadvantages. It is limited to brittle materials. Okay, it's limited to brittle materials, and it is very small material removal rate. So when you say small material removal rate, meaning that um, it's removing material in nanometers and micrometers. So in the normal range, you tend to remove a lot of material, yeah, thick chips, 1 millimeter, 2 millimeter thick chips, yeah. But here you're removing material in its nanometer or micrometer range. So that is the highlight of this process, yeah. So something that you cannot do in normal machining process. Can you remove nanometer range or micrometer range in a milling process? No way, you cannot. So you can do that in this kind of modern machining process. So this is the highlight of modern machining. So this basically concludes today's lecture. I will discuss with you on this later at 11 o'clock. See you then. Thank you. Bye.